Okay, now we're at section 2.4. It's a single slide discussion, analysis model approach to problem solving. So let's share the PowerPoint, go to the next slide. And our first analysis models were a particle under constant velocity and a particle under constant speed. Now, what do we do with these models? What is our problem solving strategy? First, conceptualize. Think about and understand the situation. Carefully study any representations of information, diagrams, graphs, tables, or photographs. Imagine a movie in your head, running in your mind of what happens in the problem, a mental representation. If a pictorial representation is not provided, make a quick drawing of the situation. Indicate known values, perhaps in a table or directly on the sketch. Focus on what the algebraic or numerical information given. Focus on what algebraic or numerical information is given in the problem. Carefully read the problem statement. Look for key phrases. Starts from rest indicates that V initial is equal to 0. Comes to a stop indicates that V final is equal to 0. A constant velocity, we'll learn later, means that acceleration is 0. That could be key. Focus on expected result of solving the problem. Exactly what is the question asking? That's very important. Oftentimes I see students solving problems that it wasn't even asked for. They think they understand what the problem is asking, and they answer it differently. So pay attention to exactly what the question is asking. I do that myself sometimes. Will the final result be numerical, algebraic, or verbal? Do you know what units to expect? Is it going to be kilograms? Is it going to be meters per second? Is it going to be meters per second squared? Incorporate information from your own experiences and common sense. What should a reasonable answer look like? If you're calculating the speed of a runner and you come up with 100 meters per second, that's a little fast. I mean, if Usain Bolt can do 10 meters per second, 100 meters per second is probably not achievable. Categorize. Simplify your problem. Use simplification model to remove details not important. For example, model, you can make the model moving as a particle instead of a car. If appropriate, ignore air resistance or friction between sliding object and surface. Most of the time, if it's important, it'll say, with a friction factor, it'll tell you. And later we'll get to drag problems where air resistance does become important. Categorize the problem in one of two ways. Is it a simple substitution problem such that numbers can be substituted into a simple equation or definition? If so, the problem likely to be finished when this substitution is done, once you do the calculation. If not, is it an analysis problem? The situation must be analyzed more deeply to generate an appropriate equation and reach a solution. If it is an analysis problem, then it needs to be categorized further. Have you seen this type of problem before? Does it fall into the growing list of types of problem that you've solved previously? If so, identify any analysis models appropriate for the problem. Analyze the problem and strive for a mathematical solution. Select relevant equations that apply to the type of situation in the problem. Use algebra and calculus if necessary to solve symbolically for unknown variables in terms of what is given. Finally, substitute in, I lost my place. Finally, substitute in appropriate numbers. Calculate result and round it to the proper number of significant figures. The final step is finalize. Examine your numerical answer. Does it have the correct units? If you're expecting meters per second and you get kilograms, something went wrong. Does it meet your expectations from your conceptualization of the problem? What about the algebraic form of the result? Does it make sense? Examine the variables in the problem to see whether the answer would change in a physically meaningful way if variables were drastically increased or decreased, even uh, if they became zero. Looking at limiting cases to see whether they yield expected values is a very useful way to make sure you're obtaining reasonable results. Think about how this problem compared with others you have solved. How is it smaller? In what critical ways did it differ? Why was this problem assigned? Can you figure out what you have learned by doing it? If it is a new category of problem, be sure you understand it so that you can use it as a model for solving similar problems in the future. And that's it. This ends our discussion of section 2.4. We will, in the next section, we will discuss is section 2.5, acceleration.